Good morning, champs. In this example, we study a very simple two-dimensional shear flow. The fluid moves only in the x direction, and the velocity increases linearly as we move upward in the y direction. In other words, the higher fluid layers move faster than the lower ones. We place a rectangular closed curve inside this flow with width L and height h. Our goal is to compute three things. First, the vorticity. Second, the circulation around the rectangle. And third, the vorticity flux through the area inside the rectangle. We begin with the velocity field. The x component of velocity is equal to a constant times y. The y component is 0, and the z component is 0. So the flow is purely horizontal, but its speed changes with height. Now let us compute the vorticity. Vorticity is the curl of the velocity field. Since the flow is two-dimensional and there is only an x velocity that changes with y, only the z component of vorticity can be non-zero. That z component is equal to the derivative of the y velocity with respect to x, minus the derivative of the x velocity with respect to y. The y velocity is 0 everywhere, so its derivative is 0. The x velocity is equal to a times y, so its derivative with respect to y is simply a. Therefore, the z component of vorticity is minus a. So the vorticity vector points in the negative z direction and has constant magnitude a. Next, we compute the circulation around the rectangle. Circulation means we move once around the closed curve and add up the velocity component along the direction of travel. We do this edge by edge. Along the bottom edge, y is 0. That means the velocity is 0 there, so the contribution from the bottom edge is 0. Along the right edge, we move vertically upward, but the velocity points horizontally. Since the velocity is perpendicular to the path, the contribution is again 0. Along the top edge, y equals h, so the velocity there is a times h. Now we travel from right to left, so the path is in the negative x direction. That means this edge contributes minus a times h times L. Along the left edge, we again move vertically, while the velocity remains horizontal, so the contribution is 0. Adding all four parts, the total circulation is minus a times h times L. Finally, we compute the vorticity flux through the rectangular area. The rectangle lies in the xy plane, so the normal direction is the positive z direction. The vorticity is constant and points in the negative z direction, with value minus a. So the vorticity flux is simply minus a times the area of the rectangle. The area is L times h. Therefore, the vorticity flux is minus a times L times h. So in this example, the circulation around the curve is exactly equal to the vorticity flux through the enclosed area. This is a direct demonstration of Stokes' theorem. It shows that circulation around a closed loop is linked to the rotation contained inside that loop. This is a very useful preparation problem for Quet flow, because in Quet flow, the velocity profile is also linear in y. The method is exactly the same.